Okay, I already recorded.
Okay, thank you, sir.
Okay, so the independence. Okay, independent. Okay, if we have even A and even B, and we can say that both even are independent if and only if the joint probability between A and B equal to the probability A multiplied by probability B. So this is the meaning of independent between even A and even B. Okay. Okay. It seems that it's not good to. Open with. Sorry. Okay. I prefer use this one. Okay, this drawing. Okay, good. Independence. Okay. Okay, and we can say the even A become independent to the even B if we have the joint probability A and B is multiplication between its probability. I mean between probability A and probability B, or multiplication between marginal probability A and marginal probability B. Okay. In this slide, I want to point out that the meaning independent and mutually exclusive are not synonym. Yes. Let's read this paragraph clearly. For example, in some context, this word can have similar meaning. Yes, but this is not the case in the probability. Mutually exclusive events between A and B have no outcome in common. Therefore, the joint probability between A and B become 0. You remember that mutually exclusive is being like this. This is A, this is B. You can see that the intersection between A and B, there is null. No. Yeah, the intersection between A and B is null. There is no member. So the probability of null, probability of null is 0, something like that. That's why the mutually exclusive between A and B, and then probability of A and B becomes 0. And in most situations, independent even are not mutually exclusive. One exception occur only when either probability A or B equal to 0. Yeah. When we have to calculate probabilities, knowledge that the even A and B are mutually exclusive is very helpful. Yeah, of course. Axiom 3 enables to add their probability to obtain the probability of the union. Yeah. Knowledge that even C and D are independent is also very useful when when we know that the C and D are independent, and then we can simply multiply their probabilities to obtain the intersection. You can, and then we have a problem. Hopefully, can make more clear the definition of independence. Suppose that for the experiment monitoring, 3 purchasing decision in example 1.7, each outcome a sequence 3 decision, each either but buy or not buy. Yeah. 3 purchasing customer. Okay. So we have to identify at least 3 box here. 3 box whether someone purchasing, yeah, purchasing, buy or not buy. Okay, buy or not buy. And then we can easily identify that the total sample will be 16. Yes, because the combination of these 3 box between buy and not buy. So actually it is equal to the 2 by power by 3. Yes, 2 power by 3. The 2 coming from the possibility that being buy or not buy, and the 3 here is coming from the 3 box here. Okay, back to the problem here. Are the event B2 that the second customer purchase upon, and N2 that the second customer does not purchase upon independent. And the B and the next is, are the event B1 and B2 independent? Actually, the B2 identifies that, or has the member being B2. B2 is like the second customer must buy. So the possibility is BB. Okay. BBN. Okay. B. Actually not B. N. BB. Okay. N. B. N. Any other? The member is?
I think that's
4.
all.
Yeah, 4. Okay. No. Okay, good. Okay. And also, we have to identify the M2, which means that the second customer must not buy. Yeah, second customer, it can be N, can be B, and B, can be B, and can be N, and B, something like that. Okay. So the total member is 4. Okay, let's check this one and this one. And the sample space. I think I make a mistake here. It's not 16 but 8, right? Sorry. Okay. Each element of the sample space has probability being 1 by 8. Which value come from? Actually, based on the equally like. Yeah. The each outcome is equally like, meaning that the probability of each outcome same. Okay. So that's why we have 1/8. Okay. And move forward. We can easily identify the probability of B2 is equal to probability N2. That's because you remember that each member is 1 by 8, 1 by 8, 1 by 8, and this one 1 by 8. So the total is 1 by 8 times 4. So it's equal to 4 by 8. Okay. How about the intersection between B2 and B and N2? You see that the member is unique, meaning there is no intersection between B2 and N2. So the intersection is null. There is no intersection. That's why the probability Bn and N2 become 0. Okay? And because of this fact, you can see, or we can state that between B2 and N2 are mutually exclusive. And logically, because the second customer cannot both are not independent. Yeah. Actually, if we have a second customer buy, we can never say that second customer not buy. So that is mutually exclusive. No correlate, no intersections. But it reveals that, shows that the joint probability Bn and N2 is not equal to the probability of B2 multiplied by N2, because you see that each marginal probability is 4/8. 4/8 multiplied by 4/8, it is equal to the 1/4. So it is not equal to B0, right? So that's why this is not equal. It means that B2 and Bn is not independent. Okay. Okay. Any question? Please write a chat and on the chat box. And move forward here. Each event in B1, actually, first we identify the member of B1. Actually, we write B and N, B and B, BBN, and triple B. Okay. And B2, we already know BBN, BBB, NBN, and NBB. As for outcome, so the marginal probability B1 and B2 is equal to 1 by 2. Okay. In this case, intersection B1 and B2, we have a member. We have a member here, BBN and B triple B. You can check here. BBN exists here, also exists here. BBB exists here and also exists here also. Okay, so the intersection between B1 and B2, we write thing like this, and the probability of B1 B2 become 1/4 plus 1/8 1/8. So you can see that the probabilities become 1/4. Okay. And this result will be equal to the probability B1 multiplied by probability B2. You can see here, this is 1/4 and this is 1/5. This is 1/2, 1/2. So it's equal to 1/4. Yeah, 1/4. Over 4. Okay. So it is equal to that's one. That's why B1 and B2 are independent. Okay. Okay. I hope it's clear to distinguish between independence and mutual exclusive. Oh, there is a question. Okay. So independent events only occur if the intersection has a value. Wait. Independent event occur if the intersection has a value. Not really. Not really. Why? You can see here. If we have the probability A becomes 0 and the probability AB equal to 0, means that the A and B become independent and mutually exclusive. In this case, the intersection between A and B is null. Something like that. Is that answer your question? But this is very special case. Okay. 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 This is a problem. Maybe you can exercise by yourself, and then we move forward to the definition. Actually, if we have three independent event, yeah, three independent event. So we can say that the all of them are independent, are mutually independent. If we can say the between A1 and A2 are independent, A2 and A3 independent, A1 and A3 independent. So that we can say that the intersection between A1 and A2 and R3 become multiplication of their marginal probability. You can see here is a multiplication PA1, PA2, and PA3, something like that. Hopefully it's clear. Okay. And if we have more than two independent, let's say that the n is more than 2 or more than 3, and then the even, so that we can write between a until n, and then all of them are mutually independent if and only if all collection even chosen, something like that. And actually the expression being like this is the for general expression if we have the n more than 3, something like that. And you can see here actually this is just multiplication between its marginal probability. Okay, this is quiz, and yeah, you can exercise by yourself. Okay. Okay. We have a new topic here. Everybody see discrete random variable?
Yes, sir.
Yes,
okay,
sir.
good. Actually, when we talk about the discrete random variable, yeah. You remember that this is the sample space. Let's say the sample space is, we can write in variable x, and the y-axis we can say the probability, right? Probability, yes, probability. And then let's say we make a experiment and observe experiment of what? Experiment throwing the coin, yeah, one coin only. Okay, one coin only. So the sample space we have only 2, right? 2 here, 2, something like that. Okay. Okay. And you see that the outcome or the element either become what? Head or tail. Let's say like that. Head or tail. Number or figure. Something like that. Yeah, it's okay lah. Number or figure. Yeah. Number or figure. And the y-axis here, it is the represent how much the probability of each outcome. Let's say we write here being small p, small p, small p. So you can guess what is the probability for the tail. Hello. What is the probability of tail if we have a probability head become p, small p?
1 minus p.
1 minus p, perfect. Perfect. Okay, good. Why 1 minus P? Because you remember that the sample space probability, yeah, probability of sample space is equal to, you remember something like probability of sample space should be 1, right? If the one outcome become P and only 2 outcomes, so actually it's easy to minus 1 minus P. Yes. So the total P plus 1 minus P is equal to 1. So it is consistent with this axiom. Okay. Nah, and then what is the discrete random variable from this figure? Actually, the random variable is this one, the X, the random variable. In a set, we can say that the sample space, but in a probability, we can say is a random variable. Actually, the meaning is same. It consists of the any possibility outcome come up. In case of one coin, we have two possibility, right? Head or tail. So we can say the random variable become head or tail. The value, yes. Okay. Between head and tail, is there exists any value?
No.
No. After tail, is there exists any value? No. That's why we can say discrete. You can see here between head and tail, there is a space. Because there is no, there is a discrete. There is something, some space between head and tail. Yeah. Maybe the more clear example being like this. Let's say this is X also. And then maybe the distribution of height of student in Faculty of Engineering, let's say between 160, 161, 105, and then 170. After you observe, make an experiment, by making experiment, you realize that from the data there is 20 students, and there is 30 students. There is let's say 50 students, and there is maybe 25 students. So the total is 125, right? 125. So the probability here is just 20 divided by 125, right? Also, the probability is 125. Also 125. Also, this is 125, right? The probability. Okay. And I want to show you that this is discrete. Let's say there is no student having a height between 165. There is no student. So that's why the probability is 0. And this position is between 160 and 161. it's really jump from this point, jump to this point, and there is no probability between them. That's why we can say a discrete. Okay. Any questions? No question? Let's move forward. You can see here, the experiment consists of procedure and observations. Procedure is a certain step to conduct the experiment. For example, you are measuring the temperature of today, maybe at 12, and you repeat again every day, and you should make the same step conducting the experiment. And what is the observation? Observation actually the information that you want to know, the temperature. And you see that maybe you realize day by day, you get a different number, different value of temperature. Maybe today, maybe around 27, maybe tomorrow, maybe 32, something like that. It's kind of random. That's why this is, we can call a random variable. Every result, we can say as outcome, of course. And then after that, assign a number of outcome, and then say, we can say a random variable. Actually, the result of the outcome, 25, 27, 32, and something like that, actually the result of measuring the temperature, this is the random variable. Yes. Okay. How we get the random variable? Actually, in general, we can classify into 3 types or 3 methods. First, from the observations. Second is a function of observation, and third is a function of random variable. Maybe the observation is already clear with the measurement of today's temperature, maybe daily temperature. But what is the function of observations? Function of observations. You can see, for example, we want to measure the surface temperature at the rocket. When we launch the rocket experience from the atmospheric pressure to the unpressure environment. I mean, when we have a rocket still on the on the world, I mean, on the surface of the world, below the atmosphere, they experience some pressure, right? Temperature pressure. But once we launch and get into the space, the temperature surrounded by the rocket become very low. And also the, how to say, concentration of the air become different, right? Maybe in in certain latitude, so rich the oxygen and something, but when getting higher and higher, more than maybe 700 kilometers, maybe the concentration of the air between more, how to say, not really relaxed, maybe not so dense, something like that. It's kind of a function of observation. When we measuring the temperature at the surface of the rocket, it's kind of a function of observations. And function of random variable, yeah, random variable is function of random variable. For example, we have a Gaussian random variable, Gaussian functions. You see that there is a function, mathematical function, and based on this characteristic, we can generate the random variable based on the function of random variable, something like that. Okay, let's move forward. Sx is the range of set a possible value. Actually, if we draw this figure, this x is a Sx. Yeah, this is set of possible value here, and x is countable, means that there is can be compute the total number of each value here, sorry. So we can easily determine the probability. So you remember that the y-axis here is probability, and for in the case of discrete random variable, we have a special name which is PMF, probability mass function. Probability mass function. So we can make abbreviation as PMF, right? The small x here, small x represent the value of here. The big X here represent the range here. Okay. So in this case, let's make this example. The probability of being x equal to 160 is equal to what? 20 by 125, right? This is the probability. Actually, it's the same. Yeah. This is x, is represented the small x. Small x is the number here, the member of or element or outcome. Yes. Okay. And again, the PMF properties. Each value, you can see the probability of x greater than or equal to 0. You can see here. You can see here. Every value here has a probability at least 1 or at least 0. 0 here. There is no probability being negative. No. So at least 0. So this axiom is hold. Okay, for this one, this is representing the sample space. Yeah, the total of the outcome here, total probability of outcome should be equal to 1. Yes. And for the even B, that even B subset of XX, let's say B equal to maybe 160 and 161. Let's say that's this is the member of B. So the probability of B equal to the probability of 160 plus 161. You can see here is 20 by 125 plus 30 by 125. Actually, if we back to this example, this one, okay, hopefully it's clear. Okay, and okay, before we going to the kind of probability, I want to show you that you can see here X, there the probability, okay, and the probabilities can be anything, and then we can characterize the kind of the type of probability based on this pattern. Let's say based on the number of element here. Also based on the pattern of this probability, something like that. That's behavior, that's characteristic that can be classified or can be say as somebody names. Let's say Bernoulli random variable. Bernoulli random variable consists only 2 possibility, like one coin, head and tail. It can be followed by Bernoulli distributions. So if one is, let's say, head has a probability being P, and the tail actually we can simply write become 1 minus P, something like that. Mathematically, you can see here for 1, for 0, 0 meaning that actually this is nothing, 0 is nothing. Actually, we can replace by head or by tail. Yes, actually, because the 0, 1 is a kind of sample, something like that. For simplicity, like a binary, 0 and 1. And others, like a binary or one coin, we don't have any other member. So that's why the probability being 0 for otherwise. Okay. And then after Bernoulli, and then there is a binomial and mathematically expressed by this formula. I don't want to more deeper about this kind of distribution or random variable. You can check it by yourself, exercise by yourself. What is the differences between them? Like a geometry, and the geometry is, you can see the pattern is lying, the slope is going down. Okay, Pascal as well, and Pascal is being like this. It's like from 0 to exponentially rise, exponentially grows up, and then after the some peak here, and then decrease gradually, but not so high the slope is not so high as before. Also, the Poisson distributions, random variable. Also, the mathematically we can express being like this. What is the random variable? Random variable is x. The probability given by these expressions. We have a value, a constanta here, alpha by power by x, and e exponential by power by minus alpha divided by x factorial. And also the Poissons, something like that. Okay, we arrive at another characteristic. We can say cumulative distribution functions. Cumulative. Actually, mathematically, we can express being like this. Usually using a big F. Big F with the x represent the random variable. The small x represented the value of random variable x. And it is equal to the probability x, big X, less than of small x here. You remember that, let's say we have a graphical graphic of, let's say, probability of something. Realize that consists of random variable become 1, 2, and 3, something like that. And then for the one have a probability 0.3, right? And for the one is 0.5, let's say like that. And for the 3 is 0.2, something like that. This is the PMF. PMF. Okay. How about the CDF? CDF, cumulative distribution function. Actually, the PDF based on the mathematics you can see here. I will draw the PDF so we can make fx, big X, small x here, and there is a round. Okay, we started one, and we have a 2 here, and we have a 3 here. Okay. You can see based on the expression here, x CDFX equal to the probability x below the x. So below the 1, what is the probability below the 1? Below the 1 probability, the probability below the 1. Anybody?
1,
No?
1/3.
Huh? 1/3? No, there is no 0.
Oh.
Okay. And after that, okay, after 1 we have a 0.3, right? And after start from 1, okay, and then no, after 1 and before 2 we still 0.3. After that going up, and we have here what, 0.8. That's great. Okay, actually at 3 is become 1. You remember that based on the mathematical, x is 1, below x, below or equal to x is 0.3. Okay. below 2 is below 2 mathematically, let's say this is a below 2 x below 2, you can write a probability x1 plus probability x2 x equal to, this is 0.3 plus 0.5, so equal to 0.8, right? Below x, yeah, below or less than or equal. Okay. Maybe we have a question here. If we have f the x equal to 1.5, what is the CDF? Anybody can answer my questions? CDF of 2.5.
Is it 0.8?
0.8. Any other question? Any other question? Any other answer? Others want to try? Yeah, Daniel answer 0.8. That's correct. Yeah, you are correct. 0.8. Yeah, because you can see here, actually 2.5 is here, right? And you can see, look at this point, is 0.8. That's the point. Yes, yes. So the graphical is like this. Yeah. Okay. Any questions so far? Oh no, okay. Let's move forward. So, for any discrete random variable x, which has a range become x1, x2, and something, and x1 and x2, x1 is less than or equal to x1, we can state following this one. First is CDF of minus infinity becomes 0. Yes, you can easily from this one. When we have goes to this point, this is minus infinity, the CDF becomes small, 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 and very small, and become 0. Okay, and as the x become positive infinity, means that in this point, positive infinity means that it's saturated at 1. Okay. And also, if x powered by this one greater, let's say x accent greater than the x, and we have the formulation that the CDF of x accent greater than fx. Yeah, it is easy to prove that. You can see here, if this is a x accent, no, if this is the x accent and this is the x, which is the x accent is equal to or greater than x, you can see here already the CDF is higher than this one point, this point, something like that. Okay, so it's easy to be proven. Okay, for x member of xx and a very small, and the a is greater than 0, and the fx minus fx minus a is equal to probability of x. And for this one also will be fx is equal to fx xe if the xe itself is less than or equal x, or x plus 1. Okay. Okay. Any questions? Okay. No question. Okay. Okay. Let's move forward to the expected value. Actually, the expected value is equal to the mean value. Mean. Yeah. The mean. Yeah. Mathematically, we can say like this. The expected of x. So equal to the mu or mean of x. And this is just equal to this is the probability of each element. This is the value of each element. This is the value. So from the example, let's say height, yeah, height, this is 20 by 100 something, and this is 30, 161, 165, maybe 6, and this is 100 something, 25. You can see here the mean or expected value will be equal to the 160 multiplied by 20 per 125 plus 161 multiplied by 30 per 125 plus 165 multiplied by 50 per 125. And for the last one is 17 multiplied 25 by 125. Something like that. This is the mean of the random variable. Also, we can call as the average of x. Okay, that's all the expected value. And then average versus expected value. What is the differences and what is the meaning? The average come from sample. Expected value come from population. You remember what is population and sample? This is a population, the real number of random variable distributions. And when we pick up some point, we have a sample, something like that. It is a small number version of population. Actually, the purpose of the sample is to simplify the populations. Let's say in application, for example, if we want to know the salary of Indonesian people, the average salary or the product domestic brutto of each person in Indonesia. Actually, the population is all of the Indonesian citizen. But it is not possible except you have a crazy rich to make all of the data from the Indonesian citizen, meaning that you want to ask them one by one for 260 million people. Is it possible? If not possible, you have to make an example, sample with certain number. Yeah. The average of sample, this is, we can say average. And the average of population, we can say mean or expected value. That's the difference between the expected value and average. And mathematically, average is just counting the number of observation here and how many data you have, and then the data is sum it up together and then divided by n. That's the average. Okay, but the expected value we can write from the its probability for each sample, for each outcome, something like that. Yeah, in some sense, in some case, the average will be equal to the expected value if you have a very large number of sample, of course. When you sampling the Indonesian citizen maybe 100 million, means that this is a really high. Hopefully that with this high number of sampling, we can depict, we can illustrate, and we can capture the real data. Yeah, of course, when we have a very big sample, we can easily determine the characteristic of the populations. That's why currently data is the new oil, because the data can be sold. The data can be monetized to make money. If somebody like a YouTube, for example, when we watch a YouTube, when we search on the internet using Google, actually we have been profiled. We are being profiling by the Google. What is the characteristic of someone? What is the preference of someone? And based on this data, the Google use for advertisement and sell your data to the company that want to market or want to sell products or goods, something like that. So sometimes you and your friend maybe sit each other browsing together with different laptop at the same time, but when advertisement is so different, it reflects the daily behavior of us. If somebody likes automotive, if somebody watch the YouTube automotive, the news automotive, usually the advertisement come up to our monitor will be related to the automotive, either a new car or new part or some car improvement, car detailing, something like that, and any other example. Okay, this is like deriving random variable. So the PMF of Kx is being like this. It's like a PMF for each value. Hopefully it's clear. It's nothing because I already explained before. So you remember for the A is equal to mean, and then the expected value, this is the random variable that we want to know, each value, multiply by its probability, and then we can get the expected value. For example, y is consists of something equations. A is constant and b is constant, and x is a scalar. So we can express the expected value become a because the random variable embed to the variable x, so we can make an expectation only on x. A multiplied by expectation of x plus b. Okay. And also the variance here, interestingly, the variance actually represent the how difference the data between the difference between the outcome. Yeah. You can see here, this is the random variable and this is the mean of the random variable, and the variance we can express by mathematically performed by power by 2 here. The differences between the random variable and its means and power by 2. Variance measure the spread of PMF. and standard deviation is square of variance. Unit of standard deviation are the same of x, of course, because it's already b square, so the unit of standard deviation is equal to df. You can see if y equal to x plus b, variance of y is equal to variance of b. If y ax variant y is equal to a power by 2 variance of x. Easily y dA is power by 2 because the variance is x minus mu power by 2. Any questions? Yes, sir. So the expected value is only used for ideal conditions. Yes, in this case, in the ideal condition is the populations. Yeah, if you means that the ideal condition is population, yes. Similarly, with the conditional probability, conditional PMF for x given b, for example, the b has a probability greater than 0. So the probability x given b, so we can write become probability x conditioned by b or given by b. Something like that. It's like a conditional probability. The probability model tells us that the probability x given b for any possible b. Example, the amount of the ith month of the year, the number of cars and crossing the JW bridge is Poisson with parameter alpha, something like that. B is the even defined in terms of x, and it is subset of x such that the x is member of xx. Based on the formula conditional probability, the conditional probability x given b is a probability. This is the joint probability between x and b divided the marginal probability of b. Okay. This is the consequence of the conditional probability, you can see the, for example, we have a px, a probability of small x. So the probability of small x given b, we have a small x given b here. Expected value of x given b, also the something like that. This is x is the probability of xb given b, and also this is similar. And for its variance, it's being like this. Actually, this expected value coming from this one. And this x is a really random variable. Okay. Any question?